Welcome back. In part 1, we explored the personality of enamel, the hardest tissue in the body, known for its brittleness and unique optical properties like fluorescence. But what makes enamel so hard? Today, we zoom in from the macroscopic level all the way down to the molecular level as we crack open enamel to reveal its chemical blueprint. Let's start with the big picture and a classic exam favorite, weight versus volume. By weight, enamel is a mineral powerhouse. 96% inorganic mineral, about 1% organic material, and 3% water. But mineral is extremely dense, so when we calculate by volume, the numbers change. The inorganic component drops to about 86 to 90%, while water is about 6 to 10%, and organic material occupies about 4% of the volume. Now to the heart of the enamel. The inorganic component. Enamel is composed of crystalline calcium hydroxide, and the formula of this hydroxyapatite crystal is Ca10PO4 6 OH twice. To understand enamel, you must understand its crystal structure. Think of a hexagonal lattice. Calcium ions form the outer framework. Phosphate groups sit within, and right at the center lies the column of hydroxyl ions. This central column is crucial because it acts as the spine of the crystal. But this lattice is not perfect. Substitutions occur. Magnesium and carbonate are incorporated early during amelogenesis, so they are found more towards the core of the crystal. So here I am not talking about the crystal lattice. See, a crystal lattice is a single unit which is made up of 10 calcium ions, 6 phosphate ions, and 2 hydroxyl ions. But here what we are talking about is the entire hydroxyapatite crystal. So it is made up of several such crystal lattices, several such crystal units, right? Such repeating units are several in this hydroxyapatite crystal. So during the early stage, when this hydroxyapatite crystal is forming, at that time, magnesium and carbonate get incorporated. So they will be found more towards the core of this crystal. These ions distort the lattice and weaken the crystal, which is why deeper and immature enamel is more acid soluble. Fluoride, on the other hand, is the hero. It replaces the hydroxyl ion to form fluorapatite. This doesn't just make the crystal stronger, it drops the critical pH from 5.5 down to 4.5. So what is critical pH? Critical pH is that pH at which demineralization of enamel begins. So from 5.5, it drops down to 4.5 once enamel converts to fluorapatite. This creates a massive buffer zone against acid attacks, which is the scientific basis of caries prevention. Now here's a quick exam trivia. Although enamel responds beautifully to fluoride, the highest fluoride concentration among dental tissues is actually found in cementum, not in enamel but in cementum. So let's look at the crystal size and shape. Initially, enamel crystals are thin, ribbon-like structures. So they are barely 1.5 nanometers thick, whereas their width is approximately 75 nanometers. Now as the enamel matures, they thicken into well-defined hexagons, reaching about 25 nanometers in thickness. Their length, however, is more than 100 nanometers. Some authors often claim that these hydroxyapatite crystals extend from DEJ all the way to enamel surface. Enamel hydroxyapatite crystals are giants, the largest biological crystals in human body, roughly 300 times larger in volume than those in bone or dentine. Because of that central hydroxyl core we looked at earlier, these crystals show selective reactivity. Acid preferentially attacks the ends of the crystals, while the lateral surfaces are relatively resistant. See, hydroxyl ion is present at the core, that's why the ends are susceptible, whereas the surface is surrounded by calcium ion, and that's why the lateral surface are relatively resistant. This is a key concept in the early caries dissolution. Next is the organic matrix. Though it forms only 1% in the mature enamel, these proteins are essential for its formation. During the secretory stage, they are divided into amelogenins and non-amelogenins. The amelogenins comprise about 90% and non-amelogenins about 10% during the secretory stage. Amelogenin is the primary structural protein. It is hydrophobic and it assembles into nanospheres, acting as a scaffold that controls the crystal spacing and thickness. So it regulates the growth of the hydroxyapatite crystal. The non-amelogenins are the functional directors, and here is how you remember them. Ameloblastin is for adhesion. It helps the ameloblast hold on to the matrix. Enamelin aids in crystal elongation and nucleation. Tuftelin is found at DEJ. It acts as the seeding protein. So it initiates the mineralization. And as you might get a hint from its name, Tuftelin is found in enamel tufts. As the enamel matures, these proteins are removed to allow complete mineralization. Amelogenins are removed more efficiently. That's why in mature enamel, amelogenins drop from 90% to 10% and non-amelogenins form the 90% of the protein in the mature enamel. Disturbance at this stage, when the proteins are being removed, leads to hypomaturation defects of enamel. Trace amounts of lipids may also be present, which may be remnants of ameloblast cell membranes after their programmed degeneration. Finally, the last component, water. Water exists in three locations. First, inside crystal defects. Second, as a hydration shell around crystals. And third, in the intercrystalline spaces. This water network acts as a highway. It allows ions like fluoride to diffuse into enamel for remineralization. Clinically, this is also how tooth bleaching works. Peroxides travel through these water channels to oxidize deep stains within the tooth structure. So these are the ingredients: giant hydroxyapatite crystals, a precisely regulated protein scaffold, and strategic water pathway. But how are these packed into enamel rods? In the next video, we dive into the microscopic structure of enamel, starting with the enamel rod. So that's all for today. I'll see you in the next one.